It's the dead of winter. You're walking along a snowy trail, minding your own business, and suddenly, something comes hurling at you, striking you square on the chest. As you wonder where that snowball came from, you look down at your palm and see the shape of a singular snowflake. It's marvelous, symmetrical, intricate, too perfect of a pattern with thousands of branches that branch even further. It's mesmerizing, confusing even. No wonder they just fall out of the sky. With a pattern as complex as a snowflake, how are you supposed to generate something like that, let alone comprehend what it is? Well, we're going to be addressing that challenge in today's video, because after all, nothing is impossible to simulate, and what better platform to do that than on Scratch? First things first, we gotta choose our approach. There are many different ways to grow a snowflake, but the most straightforward method, and the most feasible to accomplish in my opinion, is known as cellular automata. Imagine we have a grid of hexagonal cells, with a seed at the center, and every cell can either be frozen or empty, which we label as 0 or 1. To generate a snowflake pattern on this grid, let's define a set of rules to determine if we should freeze a cell or keep it empty. Notice that each hexagon in this grid has 6 neighbors. And let's say if exactly one of those neighbors is a frozen cell, then we freeze this current cell too. If exactly 2 are frozen, we keep it empty. If exactly 3 are frozen, we keep it empty as well. But if exactly 4 are frozen, then we freeze it. Once we define conditions for all 7 cases, including the one where there's no frozen neighbors, we now have a complete procedure that allows us to determine whether or not to freeze this cell. It's called cellular automata because the state of every cell depends solely on the states of its adjacent cells. Nothing is randomized, so our rule set and starting conditions controls the whole snowflake. That means we can change up our rules to generate different patterns. Now we have a solid idea, let's take a look at how we can put it into action. We first got to figure out our grid. Assigning coordinates to a hexagonal grid may seem a little confusing at first, but we can actually look at it as a regular square grid using this format. Horizontally, we arrange the hexagonal cells just like how you would a square grid, side by side. When we move down a row, if the row number is even, we start the first cell to the right of the previous row's starting cell, giving it a little bit of an offset. If the row number is odd though, we can just start the first cell in line with everything else. With this numbering system, we can generate the entire hexagonal grid using standard XY coordinates. Now we have our newly formed grid, let's take a look at how we can calculate the neighbors. For any cell at coordinates RC, corresponding to the row and the column, the direct left and right neighbors are simply r, c-1 and r, c+1, because we're just moving a column to the left and column to the right, keeping the row the same. For upper and lower neighbors though, it's a little bit more tricky, because our grid has offset. Mirroring how we devised our coordinate system, if we're in an even numbered row, the column values for our upper and lower neighbors will be c and c+1. Otherwise, it's going to be c-1 and c. Once we have our grid and rule set, we can run these operations and updates over and over again to grow our snowflake from a singular seed to a beautiful array of cells. With that, we can jump into our implementation. And warning in advance, we will be creating a lot of custom blocks for this one. Alright, so here in the Scratch workspace, I started off with a light blue backdrop with a dark blue cell that we're going to use to form our snowflake. Right now our cell is a little big because remember we're going to have hundreds of thousands of these, so I'm going to set the size to around 30% to make it smaller so we can fit more on the screen. Now we need to create a list to represent our hexagonal grid. Unfortunately, Scratch doesn't support 2D lists, but we can still flatten a 2D grid into a 1D list and create custom blocks to access and change elements within. First block we need is create grid, which creates a 2D grid with R rows and C columns, with all elements initialized to 0. I also created 2 variables, num rows and num columns, to track how many rows and columns we have in our hexagonal grid, and this is going to come in handy later on. To finish off this block, we're using a nested loop to fill up our grid, and we're going to be using a lot of these in later blocks as well. Let's go ahead and test create grid. I'm going to create a 20 by 20 grid here, and you'll notice that grid has 400 elements, which matches 20 times 20. We also need to create some custom blocks for changing and getting cells inside our 2D list. To change a cell, we first need to know where it is in our 1D flattened list, and we can get the index by simply using this formula. And if you're curious, the reason why we have that -1 after R is because Scratch indexes its elements starting from 1 and not 0, so we need to account for that. The code for getting a cell in our grid is exactly the same as change cell, except that we just need a variable to store the value of the cell that we just retrieved. With those 3 custom blocks, we've created our whole 2D grid functionality. Let's move on to the visualization. Like earlier, we're going to create another custom block for this called visualize, and that's going to take in 2 inputs, pos x and pos y, which is going to define the top left corner of our snowflake. Now, how do we visualize our 2D grid? Since we can't use clones because we're probably going to run out of clones, Scratch limits you to around 300. What we need to do is we need to use the pen tool's stamp feature. If a cell in our grid is 1, we simply stamp our hexagon there. To keep track of what row and column we're currently on, I created 2 loop variables, cur_r and cur_c, and used those to get the cell at that position. Every time we get a cell, it's saved in the variable cell, so all we need to do is check if that's 1, and if it is, then we stamp. Of course, we also need to physically move our sprite. In the inner loop, we're moving left to right, so every time we process a cell, we gotta move to the right by changing the x by a positive amount. When we move down a row, we gotta change the y by a negative amount and also reset the x to the beginning. Remember, for even numbered rows, we gotta shift it to the right. So we can check if the current row is even using modulo 2, and if it is, we have to shift the x by a slight amount, otherwise we keep it in line. That's it for visualizing our snowflake, and now it's time to test it. To make our grid visible, I changed the initial value to 1, and then called our visualize block with starting position x equals -150, y equals 150. Let's see how it looks. So that actually worked flawlessly. Not quite a snowflake yet, but at least we have a grid to work with now. The next step is going to be generating our actual pattern using Cellular automata. Time for the hardest part of this project, which is coding the generation of our snowflake. Because the basic structure of generate is the same as visualize, I stole the nested loops from that block and deleted the insides. Let's kick this off by creating a new variable called numFrozenNeighbors to keep track of how many frozen neighbors our current cell has. To avoid repeating code, let's also create a new block called checkFrozen, which checks if a current cell at row R and column C is equal to 1, and if it is, we increment numFrozenNeighbors. Here's where things get especially tricky, so I'm going to do it on the side. We have to check all of our 6 neighbors. And the 2 easiest ones are the left and right ones because we just have to add 1 to the column and subtract 1 from the column, keeping along the same row. Recall that for our upper and lower neighbors, if we're in an even numbered row, the upper and lower neighbors have a column value of C and C plus 1. Otherwise, it's C minus 1 and C. Notice that in both cases, one of the neighbors lies in column C. The only difference is the +1 or the -1. So we can create a variable called callOffset, which is either set to 1 or -1 to account for that difference in the second neighbor. Using that callOffset value, we can check if our neighbors are frozen quite easily. Let's go ahead and drag all of that into our generation block. Now that we know how many neighbors are frozen, we can create our rule set. Again, Scratch indexes its list starting from 1, but just know that all of these indexes should be shifted back by 1. A problem that I didn't address earlier was that all of these operations should be happening at the same time. But when we loop over all of the rows and columns in sequence, we're not doing it at the same time. For example, if one of our neighbor's frozen states got updated in this iteration, we don't want to use the new state to calculate our current state. We want to use our neighbor's old state. So therefore, in order to combat this issue, we need to keep track of both the old state and the new state. Since each state is represented by exactly 1 digit, 0 or 1 for empty or frozen, one simple solution is just to join these 2 states together, forming a string where the first digit is the old state and the second digit is the new state. That's exactly what we're going to do here. Using our number of frozen neighbors, along with the change cell block that we created earlier, we're going to set the value of our current cell to the old state joined with our new state, which we look up in the rule set. Again, the +1 here is just to account for the fact that Scratch indexes from 1. One last thing. We joined our old state with our new state, but we can't keep it like that, or else we won't be able to visualize our grid and continue to generate more iterations. To fix that, at the end we have to replace all of the old states with the new states, which basically involves cutting the first digit from every string, so that all of our strings are only 1 digit. Let's go ahead and test it. To grow a snowflake, we first need to plant the seed. So I changed the middle cell, which is located at 1010 in our 20 by 20 grid, to a 1. Then we can call generate and see what happens. You'll notice that our seed, which is the middle cell, was hollowed out while the surrounding cells got frozen. That makes sense, because in our rule set we defined 0 frozen neighbors to unfreeze the cell, and 1 frozen neighbor to freeze the cell. Now we can try repeating multiple times. So this is after 2 generations. You can see the snowflake expanded a little, and when we do 4 generations, it expands a lot more. Let's try 8. When we do 8, it really starts to take the snowflake form. When we try 10 iterations, it grows so much that it extends out of the frame. So let's give our snowflake a little more room by changing the grid size to 30 by 30. With additional space, we might as well just do 1 extra iteration. Now that's looking a lot more like the snowflake we all know and love. Do you notice how the sprite is creating the snowflake row by row like a 3D printer? Well, there's actually a really easy fix to this. You just gotta go into the visualize block and checkmark run without screen refresh. Something cool I found is if you drag the visualize block inside the repeat and add a wait, you can see the snowflake physically grow step by step through each iteration. And with that, our snowflake generator is officially complete. I decided to play around with some of the parameters off camera, so here are some of the masterpieces that I managed to create. Anyways, that's going to be it for this video. Hope you enjoyed watching those snowflakes grow and also learned a little bit about cellular automata and how to form those patterns. Honestly, it probably would have been 10 times easier to do this project on another platform like Unity or Python, but sometimes it's fun to make complex contraptions on simple platforms, because you always feel like you're pushing the limit. As always, the link to the Scratch project will be in the description, so feel free to play around with the rule set and the dimensions, and let me know in the comments what you managed to generate. Also, this video did take me a really long time to make, so please like and subscribe. It motivates me to keep posting more content. With that said, good luck, have fun, thank you for tuning in, and I'll see you next time. Bye!